Today we will going to learn about the fluid kinematics, which when fluids are in motion, how they are behaving or what is the equation or the governing equation we have to find out so that in the application point of view we can do this one. So let's start with the equation of motion. So normally we know from the Newton's law of second law that is force is equal to mass into acceleration. According to Newton's second law of motion, the net force acting on the fluid, let it be in the x direction. So Fx acting on the fluid element in the direction of x equal to the mass of the fluid and the acceleration in that x direction. So that is nothing but your Fx is given by m into ax. In the fluid flow, the following forces are present. Normally, the resultant of these following forces gives the fluid in the forward directions. So, one is your gravity forces, second one is your pressure forces, third one is your viscous forces, then turbulent forces and compressive forces. So, all this summation of forces is giving a resultant force in the direction of the flow. So, if we are considering the not considering the compressible flow, then the whole total equation will be coming as a Reynolds equation of motion. That is Fx is equal to Fg plus Fp and plus Fb and plus Ft. Because here compressibility force we are not taking into the consideration. Similarly, if we will remove the turbulent force, then the equation will be coming as Navier-Stokes equation. That is Fx is equal to Fg plus Fp plus Fb plus Fc. And if you neglect the viscous force, then it will be the Euler's equation of motion. What we are going to see in the next. So Euler's equation, one small derivation will be there where we will come accountability of the energy. That means when the fluid is in the flow, how the energy is transferring from one place to another place through the fluids, that we will see. So Euler's equation of motion, for these derivations, let's consider a fluid element in the streamline flow. Let that small elemental control volume which is having the area of dA and the length is ds, and it is not acting in the direction of xyz. Suppose we will take some arbitrary direction, that is the s, and then finally we will convert that s direction into our xyz direction, normally whatever the coordinates we are having. So let that s, when the direction which the fluids are flowing, so we are considering a small control volume. There, the cross-sectional area of the control volume is the dA and the length is ds, and the resultant force, the two forces here we have taken into question, one is the pressure, another is the weight force. So resultant of this force makes the fluids flow from one place to another place, that is we are considering for these cases as the streamline flow. So the resultant forces of the fluid moving in the direction of s must be equal to the mass of the fluid element and acceleration in the direction of s. So when we are making a force balance equation, we are having in the in PdA, and a little bit pressure difference will be there in the opposite side, P plus dou P by dou S into ds into dA, because there is a force we are making balance. This force is positive and this is the opposite diagonal, that is the negative, and the weight forces. Weight forces acting directly down, but along the direction of the flow it makes its component. So that component is mg cos theta. So that rho g dA ds into cos theta. That overall will give the fluid in the forward direction, that is mass into acceleration in the s direction. That mass is nothing but rho into volume, that is dA and ds, and as as usual the acceleration. That acceleration is nothing but velocity upon time, and velocity is a function of space and time. So in differential form we can write down the acceleration in form of dou v by dou s into ds by dt plus dou v by dt into dt by dt. Dt by dt is 1, and assuming the steady state we can make this dv by dt term 0. Now that is the second assumption. So finally dou v by dou s is equal to ds by dt is nothing but the velocity. So finally this acceleration for the steady state will be converted into p dvs by dt by ds. So for equation 1, what we have done here, p dA, removing the bracket, p dA minus p dA minus dou p by dou s into ds into dA minus rho g dA ds cos theta is equal to rho dA ds v dp by ds as the acceleration term. Now, so cancelling these two terms, finally minus dou p by dou s minus rho g cos theta is equal to rho v dou v by dou s. So rearranging this one, or we can divide it by the density. Minus 1 by rho dou p by dou s minus g dou z by dou s minus v dou v by dou s is equal to 0. Here that cos theta is representing dou s by dou z by dou s. This angle is ds, this angle is dz, this angle is theta. So obviously ds cos theta is equal to dz. So now finally rearranging this one, dou p by rho plus g dz plus v dou v is equal to 0. This is what we are calling, this is the Euler's equation of motion. Let's see the advanced one. That is Bernoulli's equation from Euler's equation. Normally it is thought the Bernoulli's equation is the integral of the Euler's equation. So already we know what is the Euler's equation. That is dou p by rho plus g dz plus v dv is equal to 0. Now integrating, integration dou p by rho plus integration g dz plus integration v dv. Integration of 0 is constant. So if the flow is incompressible, our density will be constant. So dou p integration will be p by rho, dz integration will be z, gz, and v dv integration v square by 2, and as usual constant. So this term is now in the form of Bernoulli's equation, but in more frequently term we can just divide it by g to whole total the equation. We will get p by rho g plus z plus v square by 2g is equal to some another constant. So this Bernoulli's equations form in the final form p by rho g plus v square by 2g plus z is equal to constant. It is giving in the energy in terms of head. That is pressure head. Second one is your kinetic head. Third one is your datum head. So all this summation of head for a flow at any point it will be constant. Any one may interchange to another one. Suppose flow is from 1 to 2. So P1 by rho g, V1 square by 2g plus Z1, whatever the value that should be available in the P2 by rho g and V2 square by 2g plus Z2. But there P1 may be greater than, may be smaller than P2. But that change may incorporate in kinetic energy head or in datum head. Similarly, the datum head or kinetic energy they can convert also to the pressure. That is depending upon the structure of the flow or where they are flowing. So these are the normally in head terms we are giving. So for this equation derivations we have taken the assumption fluid should be ideal because no losses we have considered here. And flow is steady and incompressible. Already we have seen dou v by dou t term is equal to 0. Flow is irrotational. That means it's a streamline. You see, normally when we have taken the Euler's equation, we have taken a stream tube. So what is the, this is the Bernoulli's equation for the ideal flow. Bernoulli's equation for the real flow is, suppose my flow is from 1 to 2. P1 by rho g plus V1 square by 2g plus Z1 is equal to, at the end point or second point where the flow is forwarding from 1 to 2, P2 by rho g plus V2 square by 2g plus G2 plus loss. That loss in the head form we are writing, that is HL. That loss may be minor loss, may be major loss. Minor losses, several types are there due to sudden expansion, sudden contraction, entrance loss, exit loss, bend loss, obstruction loss, whatever. But major losses, specifically it will be two types. One is your viscous loss, another is your turbulent loss. So these are the overall picture how the energy of the fluid is transferring from one place to another place. If it is ideal condition, no losses will be there. If it is real condition, then losses will be coming. So after knowing this energy conservation equation for this flow kinematics, then we will go for its application, where we are using the Bernoulli's equation. So two types of devices we are implementing to apply the Bernoulli's equation. One is the flow measuring device, another is velocity measuring device. Flow measuring device itself divided into two parts. One is your venturimeter type, another is orifice meter. And velocity measuring, it is Peter tube. Also Peter tube, same as usual, Peter and Prandtl tubes are there. So venturimeter, the construction is shown here. Pipe, in between the pipe, the venturi will be installed. So in venturi, One is converging zone, another is smaller than the pipe, the uniform zone, that is throat, another is diverging zone. So these constructions gives in such a way so that we can know the volumetric flow rate of the fluid, how much it is going through this pipeline. So here also Bernoulli equation we are used to find out what is the value of that. Normally the notation will be the Q, volumetric flow rate. So I have taken point 1 and point 2. One is at the pipe, second one is at the very nearest zone of this total system. That is nothing but the throat. So applying Bernoulli equation at the point 1 and point 2, P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Here we are considering the ideal condition. After that we will condition the real case. Then the coefficient will insert. So as the pipe is horizontal, Z1 and Z2, and finally this Bernoulli equation from point 1 and point 2 is represented by P1 minus P2 by rho g is equal to V2 square minus V1 square by 2g. P1 minus P2 by rho g reading will be taken by YouTube differential manometer, what already we have studied in fluid study. So this X difference between the left limb and the right limb of the YouTube manometer will give the P1 minus P2 by rho g, that we are indicating as H. H with respect to manometer reading is represented by H is equal to X into rho m by rho minus 1, that is the density of the manometer fluid divided by density of the flow fluid. Then V2 square minus V1 square by 2g is equal to this total piezometric head we are representing as H. So here we are finding out what is the value of V2. So V2 finally by rearranging this one we are getting A1 by root over of A1 square minus A2 square into root over of 2gh. So as we have find out the V2, then we have to find out what is the volumetric flow rate. Then at this point we are going to find out V2 multiplied by A2. So obviously we will get quantitative equation Q is equal to A2 V2 or also A1 V1. So once we got this V2, then simply A2 we have to multiply. So theoretical discharge from the Bernoulli by giving A1 and multiplied by A2 divided by A1 square minus A2 square into root over H. This is theoretical because we have not considered the losses. But as usual, flow is passing through a gradual contraction, then straightway losses, then diversification. So minimum losses will be there. That's why coefficient of discharge we have to consider here. Otherwise, it will be the 1. Coefficient of discharge normally for the Venturi it will be coming around 0.8. So when we install this type of equipment or Venturi in a pipeline, directly from the manometer reading, we can know what is the volumetric flow rate going on. Similarly, another device is there, orifice. Compared to Venturi, the orifice construction is very simple and cheap also. So here I am showing orifice. It is a circular plate with inner hole. That hole is here. This is the front view, and same way this orifice meter also act as per the Bernoulli's principle. So here point 1 is your pipe. Point 2 I cannot take at the orifice plate, because orifice plate is a harsh object. So U-tubes has to be connected from some other position rather than the orifice plate. So the narrowest region is a region where I am indicating the point 2, that is the vena contractor. So in vena contractor we are having a U-tube manometer connections. Same way, proceeding by P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Here point 2 is vena contractor, which is the imaginary one. The known value is orifice hole or orifice hole diameter. Now, same way we are going for the piezometric head difference between these 2 points is equal to V2 square minus V1 square by 2g. Let it be H, which will be related by the manometer reading X, as usual in case of Bernoulli Venturi meter. Applying the quantitative equation, that is A1 V1 is equal to A2 V2. That V1 is equal to A2 by A1 into V2. Here, this A2 it's an imaginary one, but the known one is your A naught, which is the orifice hole. So that A2 can be replaced by A naught, some contraction coefficient Cc. So this A2, A naught Cc by A1 into V2, which is given V1. So finally V2 will be 2gh plus V1 square is equal to 2gh plus A naught Cc by A1 whole square V2 square. Taking V2 comma to this side, it will give you V2 root over of 2gh by 1 minus A naught square Cc square by A1 square. So finally, as we have found out the velocity at point 2, then multiplied by the A2. A2 is nothing but A naught Cc. That means your theoretical discharge will be A naught Cc root over of 2gh divided by root over of 1 minus A naught by A1 whole square Cc square. In the form of Venturi, can I write down in the numerator A naught A1? Yes, possible. So CD will be incorporated here, where CD will be given as Cc into root over of 1 minus A naught by A1 whole square by root over of 1 minus A naught by A1 whole square into Cc square. So finally, these two equations for the Venturi and orifice both are on an approximately similar, but due to Cc availability here, the coefficient of discharge for the orifice will be lower than the coefficient of discharge from the Venturi. That is, normally it is around 0.58 to 0.61. This is two equipments normally we are using to measure the volumetric flow rate, so that mass flow rate we can easily find out multiplied by the density of the fluid. So after this, we are having another simplest equipment, that is your Peter tube, where you can measure the point velocity. The Peter tube also application applied based upon the Bernoulli equation. So here the pipeline will be there, some L type hollow tube will be inserted. There the tips of the tube will be the point 2 and somewhere it will be the point 1. So when I am applying the Bernoulli equation between point 1 to point 2, P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. But due to the obstruction, the fluids are rest at point 2. That means the velocity at point 2 is not there, only the rising height of this limb will show you the indication. If only the piezometer will be there, some h height, let it be, and here some extra height will be coming, because that pressure energy converted to kinetic energy. Sorry, kinetic energy converted to pressure energy. That is the extra difference it is taking. That extra difference, let it be nothing but the small h. So v square by 2g is given as small h. So V1 is equal to root over of Tj. These are the theoretical. If some losses will be there, then coefficient of velocity is coming to the picture. That is the V1 actual is equal to Cv into root over of 2gh. So this velocity measuring device is very simple, but here easily you can see the kinetic energy part, which is 0 here. Initially it is available here. Now it is converted to pressure head. So any Bernoulli equation is used because datum head can be converted to pressure head, datum head can be converted to kinetic head can be converted to datum head, and the kinetic head converted to the pressure head. So like this interconvertible will be possible. So that's why these are the most important equation in the fluid dynamics. Thank you.